Hello everyone, thank you very much for coming to listen to my presentation. I'd like to thank the organizers for maintaining this conference and the organizers of this session. I'm looking forward to hearing some very interesting presentations. So I'm going to present my work on modeling and simulating intensive biological systems, namely anaerobic digestion bioreactors. So this is a bioprocess that's used in particular in wastewater to break down organic matter, but also to produce biogas. And so the most common type of bioreactor that's used for this bioprocess is a well-mixed bioreactor. However, there are some newer types of reactors that consider a spatial distribution, and so basically the contents of the reactors are not homogeneous, and so there's an important research question nowadays: is what's the impact of heterogeneity on bioreactor performance? And so this leads us to consider how can we model spatially heterogeneous bioreactors, and what's really the interconnection between the biological and the physical processes at play. There are three types of models here that have been developed. The first types of models developed were compartment models. So the bioreactor is considered to be made up of zones that are well mixed, and so the bioreactor is seen as in a network or an interconnection of well-mixed zones, and so the advantages that this leads to a system of ordinary differential equations, which is simpler than the other types of models that are based on partial differential equations. Then you have some models that you could consider reduced complexity models. So they consider generally they only consider one or two spatial dimensions and no real fluid dynamics, simple fluid dynamics. And then you have a jump towards very complex CFD models. And it's only in the recent years that people have been able to couple complex computer fluid dynamics with a biological process model. And so the work I'm going to present here is a bit of a bridging the gap in between these two families of models, really, trying to develop a model that's not too complex, that we can still consider using it for optimization problems, for instance, but that still represents the geometry accurately, namely a three-dimensional model. So for this, we've modeled an upflow fixed bed reactor. So this is a reactor operated in Mexico. It's a vertical cylinder, and the fluid enters the bottom and travels towards the top. And so it travels through these thin tubes, which are the fixed bed, which help the microorganisms attach themselves to a surface and helps growth. And so this reactor is very interesting to study issues of mixing and heterogeneity, because we have first the recirculation, so from the output at the top and recirculating back towards the bottom, and then there's also a mixing system at the bottom. And so by playing with these two mixing systems, you can play with how heterogeneous or homogeneous the reactor is. So to model this, we're going to take advantage of the reactor geometry, specifically of the fixed bed, and of the fact that we have these thin tubes, and to consider that they're only one-dimensional, to reduce the spatial dimension in this section. And the second observation is that most of the biomass is actually fixed on these tubes, so it's only present in this middle section. There's very little biomass in the top and bottom sections. So the result is a model that's made up of an array of one-dimensional tubular reactors in the middle, and then a three-dimensional zones at the bottom and top. And so for these three-dimensional zones, we need to take into account fluid dynamics. For this, we consider steady-state Navier-Stokes equations. Essentially, we're neglecting turbulence and considering steady-state because the differences of timescales, right? Fluids are going to reach a steady state a lot faster than a biological system. Pictured here, we have the streamlines for the bottom section and the top section. So for the bottom section, this is the entrance, the input fluids, and here we have the mixing system, which is a pump, right? And these streamlines represent essentially the trajectories of a fluid particle. And same thing for the top here with the output here. For the biology, we use a well-validated two-reaction model. It's a simpler model compared to some of the very complex anaerobic digestion models. So in this model, we have organic matter that's transformed first by a first population of microorganisms into volatile fatty acids, and these VFAs are again transformed by a second population of microorganisms into biogas. So this model is generally used in well-mixed for well-mixed models, or chemostat type models, and so we need to take into account the specific aspects of our bioreactor in our modeling, namely the fact that we could have some crowding effects in the tubes. And so for this, for the reaction rate, we consider the classical specific growth rates that are used, but we add an inhibition function, a biomass inhibition function. So this function, what this does is it limits the reaction rates when we have high levels of biomass, essentially we're saying that when we have too much biomass in the tubes, then there's less growth. And the second thing is we need to consider a death rate, right? So for chemostat type models, this death rate is generally neglected because it's taken into account in the transport terms. So here's the full model: advection diffusion in the bottom and top section in 3 dimensions, and then a single dimension as equations, substrates. For the substrate, advection diffusion reaction, and then for the biomass, again, only reaction and the death rate. And so the link in between the different sections is going to be done with boundary conditions. So this is still a large model. So the computational cost of simulations is quite expensive. And the result is that the classical method to fit parameters is very complex for this model, for this kind of model, right? The technique of minimizing the error in between the model output and experimental data, it doesn't really work here because you need to do a lot of simulations. So instead we used parameters from a simpler model. It's still a spatial model, but a simple spatial model only considers 2 compartments. And so this model was fitted against experimental data. And then we have some extra parameters. So the biomass inhibition and the death rates were fitted very simply against experimental data. So pictured here is the concentration of the second substrate at equilibrium, which is homogeneous in horizontal directions, but there is a vertical variation, and we see that we're able to reproduce the variations of experimental data. So this is these box plots represent the experimental data that we had, and so we're able to represent the vertical variation, which is what we're essentially interested in here. Now, what's interesting with this model is that we can actually see that even if we consider initial condition with a homogeneous in the horizontal direction, we can actually have some heterogeneities that develop. So this simulation here starts with a very homogeneous situation, and eventually as time goes on, you see that because the mixing system is not perfect, there are some heterogeneities that develop. Okay, and again, these are translated in the biomass that are different. And then what we can do is we can look at the impact of the mixing and the impact of heterogeneity on the biological activity. So here what was presented is the values at equilibrium of the first and second substrates, and also of the biogas flow rate at equilibrium, and as a function of the recirculation rates. So the standard conditions normally for the experimental validation, for instance, are 150 liters per hour. And here we can see clearly that actually with a lower recirculation rate, the reactor is more efficient, we have less substrates coming out, and we have higher biogas production. But, however, if we actually look at the profiles of the substances inside the reactor, you'll notice that for the low recirculation rates, we have very high levels of biomass, unrealistically high levels of biomass, and essentially this is what explains why you have higher production. If you have more biomass, you have more production, you have more depollution, decontamination. But really, if the model reaches high levels of biomass, it's really because we're not taking into account inhibition very well. And you can see this if you look at the growth rates. And this is one of the issues of doing experimental, of fitting parameters, because the values for which there was substrates were only very small. And so the fitted parameters here in blue, we can see that, for instance, for the specific growth rates, there's really there's no inhibition. And again, so we were only considering a very limited amount of biomass inhibition. And so actually, if we considered more inhibition, so the red curves, if we consider the red curves here, more inhibition for biomass and in terms of substrate inhibition, what we obtain is a completely different picture. So with these values, you can see that actually with more recirculation, we have a better performance, right? We have more biogas produced and more less substrate coming out. And so again, we can see this as well in the profiles. What's interesting to see is that in this case of inhibition, actually the profiles are a lot more homogeneous. So as conclusions, it's interesting to see that this kind of simpler models can represent the physical variations within the reactor. It's very interesting to see the impact of heterogeneity. It depends on the growth function. So we need to have a bit more experimental data to really represent inhibition correctly and give a firmer result on the impact of heterogeneity. So thank you very much for your attention.